Good morning, Chem students. We're here on a Friday morning, and hopefully you are finding some time to listen to this very short little podcast on ionization energy. And ionization energy and electron affinity, atomic size, they're all going to fit together in terms of looking at how our compounds form. So the first thing that we're going to talk about is ionization energy, and you can read that it says the energy required to remove an electron from an atom in the gaseous phase. Well, we have to keep in mind, remember that electrons all have energy, the atom has energy, and so we are going to have to make sure that we take a look at how this is going to come about in terms of our energy exchange. So we are going to remove an electron from an atom, and you can see that I have element X, whatever it is. I'm going to add energy into the system. If you think about energy coming in, you should remember that that is going to be endothermic. That energy is going to come in. There's too much energy in the system. The electrons are jumping around. If we were in class right now, I'd make you guys come up and be little electrons and be jumping around, and someone else is trying to come in. Well, if that's going to happen, something's going to get ejected. And what's going to get ejected is an electron. And when that happens, that electron leaves the metal, usually a metal, with a positive charge. So if I am lithium, and if you guys think about lithium, it's 1s2 and 2s1. So it has 3 electrons. Well, it's going to lose that 1 electron pretty easily, but what's going to happen is this 520 kilojoules of energy is going to come into my system, and then that electron is going to be lost, and I have lithium in as a positive ion. It has become a cation. So most of the time, these atoms that are going to become cations are often going to be metals. And the reason for that is that it's easier for them to lose those electrons to become very stable and be stable like our noble gases. So when we talk about a first ionization energy, like it says right here, we are talking about removing 1 electron. Logically, second ionization energy is going to be removing the second electron. Well, if you take a look at this, now with this +1, if I take a look at lithium, its electron configuration is 1s2, which is a noble gas configuration of helium. If I take a look at its first ionization energy, you can see that it only took 520 kilojoules per mole of energy. Look at this number. Wow, that has really increased. Well, you should be thinking why. Well, the reason why is, does this really want to remove another electron? Of course not. It wants to stay here. It's stable. It's happy. It's in its state that it wants to be. And now we're going to disrupt its little stable place that it is. So it's going to take a ton of energy to do that, to remove another electron. If I remove another electron, it should make sense to you that the charge is +2. So in terms of ionization energies can be explained by electron configuration, as I was just showing you. If you have a more stable configuration like a noble gas, the ionization energy is going to become very low. Like if it's going to get to this configuration by becoming a noble gas, it has low ionization energy. It's kind of worded weird. If it's less stable configuration, meaning that its result is going to be less stable, then it's going to take a lot of energy to do that. So this was in the first example that I showed you with lithium, and this is the second. Again, we can see this again. If I take a look, here is my electron or my orbital diagram. The first ionization energy to remove that electron, pretty easy. Bring in 520 kilojoules of energy. But to remove one of these two in the second ionization energy, it's stable now. It doesn't want to do that. It's going to take a lot more energy. The same thing here with magnesium. If it's going to lose its first electron, either one of these, it doesn't matter which one you choose, but it's going to lose this first electron pretty easily. You can see the second electron, not a whole lot more energy is needed to remove that second electron. You look on your cation and anion sheet, you recognize that magnesium has a +2 charge. That's what it needs to become stable. So it has noble gas configuration now. That is shown here. You can see that all of these sublevels are full. It's going to take a whole lot of energy, look at that value over there, to remove the last electron that was entered. And you can see here that the parallel spins are here, and then it went back. So this last electron is the last one that entered this orbital. Very difficult to remove, and that just does not want to happen. So if we take a look at the positions of our periodic chart, the ionization energy should make sense to you. Here is magnesium. Loses those 2 electrons, and now it has neon gas configuration. The other one I showed you was lithium. Lithium loses that 1 electron, and now it's going to become like helium. Now, it talks about general trends. So general trends, as I go across, the ionization energy is going to increase, meaning I need more and more energy to remove that electron. Well, that corny little clip that you guys saw, remember that fluorine is highly attractive. Is that what it said? Well, it doesn't. If it's attractive, it means it wants to gain electrons. It doesn't want to lose any. And it does that because it's very close to the noble gases. So this ionization energy, remember the energy to remove an electron increases as I go across the period, and that's because that Zeph charge becomes stronger and stronger and stronger. And remember, that is adding protons and electrons in the same energy level, so that is going to increase, meaning making it very hard to remove that electron. It's going to decrease as I go down, meaning easier to remove. And remember, electrons are entering higher energy levels. Those higher energy levels make it easier to remove an electron. So higher energy, forgot to spell there for a second, energy levels. And so it makes it much, much easier for them to lose these electrons. You can see on this side of the chart especially, lose 1 electron, lose 2 electrons, very easy to make it look like a noble gas configuration. And this last little chart that you guys are looking at here, you can see that within a period how the ionization energies are high when they're a noble gas, go down, lithium, sodium, potassium at the start of a period, it's very, very low, increases as you go across, increases as you go across. And that's the trend that Mendeleev was looking at when he is starting to place these elements in certain periods. All right, that's it, ionization energy. Bring this information with you to class on Monday, and we will put it to work. Have an excellent day. Make sure you get some rest and do something fun for yourself. I'll see you soon.